we have so many different views and they're related one or the other. So it's actually time to start a panel, and David Warren will take over. And for the people who had the questions and other discussions, I see these chats. I actually am very slow at reading and writing, so you can speak up.
There's a second channel on in the chats on
yeah.
discussions, points people want to make, which is an interesting, good thing to do. Except I have two eyes, but I only one brain, so it's hard to. Okay, so.
So can I?
So, okay. So let me open. Okay, so the panel. My idea for a panel is that we just ask. I'm most interested in questions that cross. That everybody spoke. All the speakers spoke some aspect of. However, by all means, specific questions to speakers, and of course, speakers can ask other speakers and ask themselves stuff. So this should be more or less free-ranging. We seem to want to talk a lot, which is good. So let's get started and go, Paul. You seem to.
Okay, cool. So I'm going to be, so just a couple of observations. One is that I think the point about invariants is that Leslie made is very important. And indeed, I mean, you specify the invariants, and the whole idea would be then the models that are induced by those invariants are the ones that are interesting. And so we're discussing about why logic has deficiencies. And I think especially even the previous talk by Patrick. So one of the problems is that, and I'm giving away some of the points I'm going to make during my presentation during the break, is that logic really does not have its own truth predicate. Meaning, if a proof fails, then what do we do about it? We can't do anything about it. Whereas as humans, if a proof fails, then we use that failure to take some other action. And unfortunately, that cannot be expressed in logic. So that's where negation as failure, and Michael is here in the audience, becomes very important. So I think the goal should be to come up with logic that can simulate sort of the human thought process, because as humans, we're able to do all this. And so negation as failure and all these things help. If we add negation as failure, then we're able to reason about failure of proofs, and we can take actions. And I think then the power increases. A good example is that I give is, for example, you have a bunch of cities connected by roads, and you want to reason about reachability. So you write a very simple transitive closure program. And now if you want to know if city A is connected to city B, you pose your query, reach A, comma B. But if the proof fails, you cannot say that within the logic, you cannot say that these cities are not connected. You need separate axioms for unreachability. But if you have negation as failure, then you can immediately say, well, if the proof fails, then maybe I'll take a helicopter instead of driving. So we need to, the logic has to have its own truth predicate, essentially.
Okay.
To become more useful.
Anybody want to respond? Any of the speakers want to respond?
Proof of failure is not a logic. It's a computation mechanism. So there is a confusion here between a logic, which specify things, a proof which are different from logic, and the computation mechanisms. Maybe some logic can speak about the three, but the first order logic never speak about proofs.
Of course. So we have to move out of first order logic into other things. Yes.
It's also related to induction, I think. And part of it is that induction is beyond first order logic.
Oh, also, yes. I did not mention this in the 4 points. So that's a bit a problem. That is, we cannot reduce everything to logic. And to represent information, I think logic is not really a good representation of information. For example, if you want to specify a transition system in logic, it's painful. You have to have prime and non-prime to speak about time. That's a trick. That's not fundamental. And another example was a Richard example. When you have things like unification, suddenly he said, oh, I need independent substitution, but he never explained why. It was because it failed. But there is a nice explanation. It is symbolic terms are abstractions of sets of ground terms. And if you do that, you will get the exact algorithm and you will have idempotent substitution because of the abstraction mechanism, which is to guarantee uniqueness. So I think it's this structure is coming from another structure, and in logic, it's very difficult to have different structure to represent different things and at different level of abstraction and to link them. And in TLA plus, it's more or less predefined how you link different models. I think I'm not so good in TLA, but there is no mechanism in TLA to do this. It's done specifically for each instance of TLA.
Actually, in the unification proof, the failure of the proof suggests the addition of idempotence. This is not done within the theorem prover, but there's a clear, to get the induction to go through, it's necessary to show that the algorithm eliminates variables, which is part of the idempotence problem. And also we do induction within first order logic, like SNARK is a first order logic theorem prover, and we do it by reifying the it's well-founded induction, and we reify the well-founded relation. So it is possible, and also it is possible, even within first order logic, to have a formalized meta theory, so you can reason about expressions and about proofs. You could have proofs be objects in a first order theory and reason about them too.
Yes, but that's not part of first order logic, that's a higher order logic.
You have no, you can do it within first order logic, just introduce proofs as first order objects. And
yeah, well, incompleteness does that kind of reflects proof in the logic, right? But it stands that the full induction requires higher order, second order logic, right? Full induction. Now, if you're not doing a full induction, you're limiting the sets to certain kinds of sets, then you can do it in first order. But full sets, you don't. I have, if I can jump in, I have a question that for Leslie again. Sets are it's a very powerful data structure. Maybe I shouldn't think of it that way, but an issue around sets is that depending on how you use them, there are very different ways you might implement them and get different complexity out of that. So I've always thought that algorithms ought to imply a complexity, right? That's what you want to do. But if you say, okay, I'll use a set any way I want, you might not. How do you specify the special implementation of the kind of set you need and the operations on it to guarantee the complexity that you're going to argue that your algorithm has? Does that make sense? You're muted.
Yes.
You unmute.
Unmute.
I'm sorry. Well, I mean, your question makes sense, but it's like asking me, well, if I'm writing Euclid's algorithm, what does it tell me about how I should implement my integers? Well, I mean, it may be an interesting question, but it's completely orthogonal to the question of Euclid's algorithm. Because, for example, if Euclid's algorithm, if subtraction happens to be a very expensive operation, well, that means you might have, something else instead of Euclid's algorithm. But, Euclid's algorithm itself doesn't tell you that.
Yeah, but some algorithms, that you're right. I mean, I understand that algorithm, but the algorithm that depends on the stuff you're doing in the set, you know, the operations you're doing on the set, where it really does make a difference. It's not just a sub. It's special cases, you know, special ways you're using a set that can be very efficiently implemented or not.
Well,
that seems to be more intrinsic to the algorithm. It's not just a sub operation that you're using.
Like convexel or polyhedra, for example.
I'm sorry?
Convexel of polyhedra is an example.
Oh.
If you don't have the good representation, you are not going to make it.
Anyway, that's just a point about an algorithm, and my sort of saying that you can sort of use any mathematical primitive operation you want strikes me. Like I say, it's to understand the concept behind the algorithm, but to get the complexity might not be so obvious is what I'm trying to ask.
The definition of complexity isn't obvious. If you have a definition of complexity, you say, you know, here are these operations and each one costs a certain amount, then I can simply add a variable to my algorithm, and then, you know, the complexity is a partial correctness property. You know, when you finish it, that value, that number that you've counted is less than n, but you want to separate the concerns. That's the whole point of an algorithm. An algorithm, well, you now not want to talk less about algorithms, because in some sense you're really talking about building systems. Because when you're talking about how fast does it compute, you know, that depends on, you know, what your computer is doing. Now, is the algorithm supposed to tell you what computer you should be using? No, but on the other hand, an engineer who's designing an algorithm should understand what computer he's using and should understand whether subtraction is a very expensive operation or not. And what I find in practice, engineers don't expect the specifications, the TLA plus specifications they write, to tell them about the efficiency of the algorithm. Now there is actually, it's not quite accurate, but they know that they're interested. What TLA plus is going to do is to say, does this algorithm do the right thing? And they know they have other tools, or other ways of thinking about how fast is it going to do it. Now, in fact, it turns out there's some work, you know, someone is doing some work on trying to actually use the model checker to get, you know, not worst case estimates, but average case estimates, you know, performance information. That looks promising, but that's just because you've got a precise specification of the algorithm, and you can put in it, you know, information about, you know, sort of how long does this thing take. So you can use the same tools, which is nice, but it's sort of it's an orthogonal issue. And, you know, the way you succeed in something, trying to solve all the world's problems, you know, because, you know, you're not going to give an engineer one tool that he's going to use and it's going to, you know, generate, you know, optimally efficient microcode. You want a tool to solve particular problems. And the problem that I'm concerned with is, does this thing do what it's, you know, in some sense, you know, give you the correct answer? And whether it's efficient, whether, you know, how many computers you need to execute it, that's a separate issue. And I don't want to complicate one to, you know, the way of answering the first problem in order to try to solve another problem as well.
I thought I had a question, but I saw Peter was before me. There was a list, but Paul should be after me. I didn't write it in queue. So Peter.
I have a question for the panelists. So I was very intrigued by Patrick Couzeau's talk, and that logic is so limiting and time is painful in logic. Don't use logic for making proofs. So my question would be, Well, I guess then, but logic has lots of advantages, first order logic. I mean, truth, things that are true stay true, it's monotonic. So I guess what you want is to use logic wherever you can, and only in those places where you can't use logic to use some other approach. Is that reasonable?
That's a question to me.
To all
Yes,
panelists, I
maybe
guess.
to the other panelists.
The problem is that there is not a continuum between, for example, a logical specification of a convex hull of polyhedra, which is just a simple convex hull of definition in one line, and an algorithm. And logic will be simple at the beginning, but you see, you change the language and the mechanism of reasoning from the beginning to the implementation. And this lack of continuity is the problem for me.
I mean, there's steps. I mean, there's not a thing for every intermediate point, but there is a kind of spectrum, right? More and more algorithmic, more and more logic.
Yes, but what is the common language between these? Apart from set theory, I don't know what.
Well, maybe it's set theory on one side then, and algorithms that interact with the real world on the other side.
That's what I do. That's what I do. But
both worlds is you try to stay in the easy walled garden of logic as much as you can, and you only leave it when you absolutely have to.
And I would say that when you leave, that world is also logic, right? So, but these are all connected.
You're not yet getting all the good properties anymore, huh?
Yeah, sure. You may not be. And so then you get into the realm of, perhaps non-monotonic logic. But I think these various things are there, and then you can put them together. And that's, I think, the approach that will work.
But logic programming and functional programming have always somehow assumed that. I mean, Church-Rosser theorem does not talk about interaction with the real world, but a program has to do that. But you still want to stay as much as possible in the beautiful confluent walled garden and only leave it when you really have to. Huh?
Correct. And you may have many such gardens. And the nice thing, I think, is that answer set programming actually provides a way to put together all these gardens.
Okay, that's nice.
But then you have to commute. But then you're using logic. You need to use logic as a intermediate language, a conversion language, and
as well. Yes.
Patrick talked about that and the difficulties of that as well. Paul, I think, Paul Thoreau had a question that maybe he could.
I would also mention about the gap between what mathematicians write and the logical proof for that is definitely huge. But part of that could also come from I would say a little bit the rusty logics that we are using here. Today's, let's say, Coq and Agda, proof assistants, they do not use anymore this non-constructive first order logic. They use intuitionistic logic under the hood. So there's no such thing as a double negation from which you infer something. And I would say that by having a constructive logic, and then on top of that, of course, a number of rewriting of set theories, like in dependent type theory, for instance, and some of the related formalisms, you might get a more narrower gap between the specification, which in predicate logic, in first order logic, is non-constructive, basically. In this case, when you actually prove something, you like in an existence proof, you actually show this is the object, it exists, here it is, versus, oh, this might need to exist because otherwise something wouldn't go well. So the constructiveness is another aspect that is very important, I guess. And, modern day theorem provers move closer and closer to computation, basically because they are becoming constructive.
I have a comment on this. When the people try to prove a static analyzer with Coq, They cannot define what is an abstraction function. And so that's because of constructivity. And so what they do, they define a relation and say, oh yes, it's a relation. And each time they use it, they have to prove that it is a function. And after 2 times, you abandon. And so you can prove soundness of our logic, but not completeness.
Leslie had a question that he wanted to ask the general group, I think.
Well,
Carl and
actually,
Annie have questions also.
I don't want to ask. I'm going to read a question. The title of this panel is Logic and Program Specification. Where has it failed? And I'd like to ask the other panelists, where has it failed?
And so if I
David's question, yeah.
While people are thinking about that, I can give you the background for this question. I was trying to be a smart aleck and coming up with all these questions to play the devil's advocate a little bit. So these are just out of my, like I say, my smart aleck brain. But if people have comments on that, I would like to hear them. And by all means, say this is a ridiculous question if that's what you think it is, and explain to me why it's a ridiculous question.
No, I think so. If I can jump in, so that's what I mean. It's an excellent question, and I think as Peter pointed out, we have all these things, beautiful gardens that can be modeled using logic, and then you have to have a logic that puts together these gardens. So that's what we got to have to make things work. And as I said earlier, I think answer set programming actually has the answers, I believe. So we're working on this interesting project, but what we're trying to say, trying to figure out, given a sequential algorithm, can I automatically generate a concurrent algorithm out of it? Just as a human domain expert would do, with an understanding of, so you have the axioms of concurrency, you have the axioms of how locks work, you have the axioms for the data structure. So from these, can I infer the concurrent algorithm for a concurrent operation? And I think it's possible, but you have to come outside of logic a little bit. And if proof fails, then what do you do? So for example, if an invariant fails, what do you do in those situations? You have to have actions that you will take. And so I think, in my opinion, answer set programming and non-monotonic logic is a good answer to make logic succeed where previous attempts have failed.
Any comment?
Okay.
Other comments?
What answer, Richard? Do you have an answer? No.
Oh, to the original question, I thought one reason logic is not more widely used is that people don't find it congenial.
No, the question is, no, where has it failed? Not why has it failed, where has it failed? That's the question.
That's a fine distinction, but I thought the fact that people don't like quantifiers and other constructs in logic makes people like software engineers reluctant to use it. They can understand iteration in a programming language, but they at least claim not to understand quantifiers in a specification. And I thought, like Bob Kowalski's use of English as a specification might be a way around this everyone knows natural language.
But again, you're getting to, how to stop, how to unfail it. I just say, where has it failed? And you just sort of, almost, we're sort of touching on it, because, see, my answer to that, and the reason I agreed to be on this panel.
Great, I was going to ask.
At Microsoft, there are, maybe 20, maybe 50 people who use TLA+. There are 100,000 people who work at Microsoft, maybe, actually, I don't know how many, maybe 50,000 programmers. In 1967, Bob Floyd wrote this paper called Assigning Meanings to Programs, which probably started most of the work that's being talked about here. Of those 50,000 programmers at Microsoft, how many have any idea what Floyd said? I would say maybe a couple of hundred. And I think that's a complete failure. And I don't hear anything going on here that seems really interested in addressing that failure. And the thing that has disturbed me ever since I've started thinking about what's called program verification is there has been an attitude among the computer scientists working on it that I've seen, is that their goal is they want to make absolutely correct programs. And they want to make sure that, so if there's any chance of, so you have complete mathematical proof or something of your program, and anything less than that, oh, it's a waste of time, they're not interested in it. And meanwhile, people who actually write programs look at what they've done, or what Floyd did, and said that, oh yeah, this is great for little toy programs, but it's not going to work for this 20,000 line program that I'm writing. So it has nothing to do with me. And so what has been a complete failure is the ability of this community to tell those 50,000 programmers at Microsoft what they can use, what Floyd said, in their daily programming.
Why aren't they taught that?
And to me, it seems absolutely criminal that you have 50,000 people writing code, and hardly any of them even understand the concept of a loop invariant.
Okay, I have an answer. I can answer.
That's why I think it's failed, and I'd like to know what can be done.
You know why it's failed, Leslie? Because computer science curricula are money-driven. People pay money to send people to college, and they want something which is directly industry applicable, and the students will not learn mathematics. They will learn programming, hands-on projects, low level, and they will not learn how to reason because the parents and all the other associations will not let the universities do that. And that's a big problem in the United States, slightly less in Europe. But my students, when I teach them logic, they have a hard problem understanding quantifiers. And how do you take a thing like a quadratic problem and represent it in quantifiers? That seems very simple. They have a hard problem with that. And students are not learning to reason mathematically. And this is a very big problem in the United States. And the reason is that curricula are money driven.
Only in US.
There you go.
Can I ask you a question, actually, for Leslie, but everybody too, actually, and this is not my idea, but I'm actually so glad that Leslie ended with his reasoning for we're not teaching students invariance. So when I was a graduate at Cornell, actually, I didn't know that at all. I wasn't taught that at the Peking University, at Tsinghua University, but Cornell was really strong. They were they are really the worshippers of Dijkstra, or some of them, Norgate agrees. But there are also some newer students or some other people who were telling you, what invariance and that old stuff never went anywhere or something. But anyway, so I had this mixed feeling. Maybe some people didn't like it, it didn't work. But until, of course, I realized all the optimizations we do about the differentiation of, incrementalization program is starting from invariance. But my question is this: I didn't know until just a few years ago, actually, a Neil Nerode told me this, and I was thoroughly enlightened, sort of, but still so much. But anyway, so he was saying all these invariants, they are conservation laws in physics. And so there's the famous Noether's theorem that says every symmetric differentiable function has a law of conservation. And I had all these years of completely vague feeling. After I studied that a little bit, I was so amazed. So all this thing about non-determinism, there's a high level thing Leslie was talking about, and sets and so on, that's a kind of a symmetry. Of course, I know differentiation, that's what we do in incremental phase. So I was wondering what Leslie thinks about that, because I didn't hear any other people telling me about it. Of course, everybody else who, grew up in math and physics. I don't hear,
I'm sorry, I want to defer this for a second. And Peter, I think, illustrated what the problem is. I was talking about loop invariance, and he said, well, they don't know about quantifiers. Did I say, you need a quantifier to write a loop invariant? You're just making the assumption that a loop invariant is a formula. You can write a loop invariant in English, but no, your whole instinct is, oh, I did loop invariant in English. Oh, that's a waste of time. It's not a waste of time. If people can't learn to write a loop invariant in English, what motivate, or the importance of that, why should they be motivated to learn what quantifiers are?
That's all part of the issue. Those variables in there are not free. They exist in a certain context. People do not understand that. Those variables.
No, you do not understand. No, you do not understand that the concept of an invariant is not dependent on any logic. The concept of invariant is a simple idea. And why isn't that being taught?
Yeah, why isn't
you don't need to have a math course to even teach that.
Why isn't that
not being taught? Because you
yes.
haven't managed to explain that to your colleagues who teach the programming course.
Well, I teach it in my courses, but I'm not in the US.
No, but not just US, but I think the problem is that teachers themselves don't know it. So maybe the people here, when we teach invariants, but whether informally or formally, but in general, yes, invariants are not taught. I should add one thing though, that there are certain groups like people in avionics. I mean, they understand the issues related with people who build avionics software with verifying code and verifying what they write. So I think there are people, you could argue that an average programmer in Microsoft writes programs that if it breaks, maybe, you know, your transaction will not complete or something, you know, it may not, your search may be imperfect or something. So people don't care, I guess.
I was going to say, exactly that point. Let me just say that my experience in programming in, not Microsoft, but in the company is we don't allocate enough money to build good software. We don't have it, right? So we build lousy software. And we build lousy software because it's good enough for the things that we're trying to do. Yeah, it crashes every once in a while, but it's really just getting data from something. And so if it crashes a little bit, that's not good. It's bad. We get wrapped on our knuckles, but we're not gonna double the cost to try to make sure it's always right.
But wait,
can I inject something?
Not because I have any desire to do it, but because it saves me time. It makes it easier for me to write a program. So we're not telling them to do something that's going to cost more. We're telling them to do something that's going to save them money.
Yeah, and
I think
it's amazing, isn't it? That is completely true. But despite that, they don't do it. They don't.
So let's the question is why?
Carl had a question also.
To them how they can save money by doing it.
I think the problem is a little bit deeper than this. I've actually been talking to people about it. Part of the problem here is, if you look at the computer science curriculum, there is not enough, in my opinion, for example, discrete math taught at the primitive level. So look how we educate our computer science students. We have them take about 6-7 courses on calculus, algebra, differential equations. Some of this material has to go into a very solid training on discrete mathematics early on. I think actually undergraduate students in computer science should start by having discrete math 1, 2, and 3, where some of these concepts are taught there. We don't do that. And a lot of places, they throw the discrete math course to a math department. In my opinion, to really have students start thinking this way and have this solid background, they need to have a solid sequence of discrete math where some of these concepts are really taught early on. We're still doing this the way it was done 50 years ago when computer science was part of engineering and we inherited all of the math education from other engineering fields. We have not adopted to that. I had the luxury of being trained at Stanford, and that wasn't the situation. I was taught logic 1 and 2 as, you know, at the undergrad, they were at the undergraduate level, and that made a big difference. That doesn't happen in a lot of places. I don't know if it's still happening at Stanford now, but again, I think instead of calculus 1, 2, and 3, you need discrete math 1, 2, and 3 at the undergraduate level, and that's not happening.
I would go even a step further and say in high schools.
We're at the end of time. So